Hello and welcome to Porous Media Tea Time Talks, a webinar series organized as part of the Interpol Young Academy, dedicated to promoting research by early career PhD and postdoc porous media scientists around the world. Today, we have a dedicated session for the Skoltech or Skolkovo Institute of Science and Technology in Moscow, and we are delighted to have two excellent talks lined up here. And we are happy that you are with us today. We are excited to bring this series of webinars to researchers, students, and professionals working with porous media sciences to gain insight into the latest advancement in the science and technology. And today we have two talks focused on the microfluidics. Without further ado, I would like to invite our first speaker. Our first speaker is Margarita Latypova. She has a PhD in geology and mineralogy with an expertise on R&D, specializing in the integration of microfluidic technologies in the business production processes. She is involved with the high-tech development in the intersection of industry and the fundamental sciences, and she is working to produce and to develop microfluidics for the oil and gas industry, chemical industries, and biomedical sector. Thank you very much, Margarita, for joining us today, and the floor is yours.
Thank you very much for invitation. So the topic that I would like to tell you is the methods of modifying the void space wettability in microfluidic chips, from chemical modification methods to crystallization of metasomatic minerals. And actually the second part should be told by Yury Kadomsky, but actually he's absent. Sorry for that. So I will tell his research. First of all, I just would like to introduce a little bit about our colleagues. We work in the Skoltech laboratory, the company Lab Advanced. So we're just developer and owner of microfluidic research technology that's founded in 2020 by Skoltech employees. And we just provide microfluidic research service and equipment to help just science to improve the sustainability and the process and reduce operational costs for the business. So we have four main ways to work. First of all, oil and gas industry, then synthesis of low tonnage chemistry, biomedical areas, and synthesis of pharmacological agents. So once we've just all of the research we will present you just done in our equipment. So the pumps that we do ourselves in the university, the microfluidic cells, and flow through microreactors, our hydraulic lines and control units that we've just used to work with the pore space, and microfluidic chips, which we can just create custom void geometry design and fabrication ourselves, and just modify the wettability of the porous structure. So the first part would be about this modification of the wettability. How do we do it? Using just chemical modification methods. So the main problem is that the wettability is a key of four petrophysical rock characteristics that governs capillarity pressure, permeability, multiphase fluid distortion, and many different factors. So wettability affects the efficiency of most hydrocarbon recovery technologies. And in our research, we always try to take the core space of the real rock and make the same one inside of a microfluidic chip. So we need to make the same pore structure, not just geometry. We need to repeat the wettability too. So the wettability state of the rocks depends on a range of factors, including the mineralogical composition of the reservoir and many interactions between hydrocarbons and the porous surface of the rock. So complex reservoirs are often characterized by heterogeneous or selective wettability. So the best thing we just the best option we just found is to take the chemical agent included inside of the chip and change the wettability of the pore space. And in this research, we will show you how did we do it with the sealant. So there is a general mechanism of oscillation of a siliceous surface. Our chips, microfluidic chips, they are made from silicon surface. So I will not tell all of this process, but at the end we will achieve just the covalent bond with the surface of siliceous plate during drying. And here the whole our experimental workflow, what did we do? We just took 4 plates, first of all, before the microfluidic work. They are quite different because all of these plates, siliceous plates, have been done by different types of plasma treatments. And then we've just and the borosilicate glass, because on the top of this chip we always have the glass. So then we've just measured the surface roughness using the atomic force microscope, and we've just measured the contact angle on each plate, just to understand, do we have any difference in the contact angle in different plasma treatment siliceous or not. Then we just cleaned, did some immersion, did flushing and drying, and measured the contact angle after modification of sealant. And then we just were trying to test the coating durability. We just mixed the plates after modification and watched what would happen with the contact angle. So in our fields, we just used microfluidic chip 2, and microfluidic chip was fabricated on silicon wafer using microelectronic processing techniques. So we've just it is just the structure of the real rock. We've just investigated it through microtomography and did the same structure inside of the chip. It is just the real the real core reservoir, oil and gas reservoir. So here you could see the hydraulic diagram of the microfluidic system. There are some valves here. There are our pumps. There are just a back pressure regulator and a couple of pressure sensors, and the microfluidic chip and the special microfluidic platform that keeps us to save the temperature and the pressure in the whole system. So here are our pumps. Here is the microscope that we have been using just to search what happens in the chip. And we just, first of all, it was very important for us to understand how just the different type of plasma chemical treatment of the siliceous influence on the wettability angle. And here are four siliceous plates that I was talking before, and here is the contact angle on the plates before the surface modification. And here is contact angle on the plates after surface modification of the silane. And we could see that even before we had some differences, like somewhere is 62 degrees, here is 42. After modification, we have almost the same contact angle. So we don't really care about the type of the chemical plasma treatment. So it's important for us to know that the final contact angle after modification is not very it's not very important which type of chemical treatment we've just choose before. So here is the result of hydrophobization of silicon wafer surface with the silane. There is an average contact angle values for each silicon of glass plates. We had 4 silicon plates and 1 glass. And on the picture A, you could see that this is without preliminary modification, like silane, and that's all. So B have been done with preliminary treatment with acetone and potassium hydroxide. So we did first modification of it, and then we just put it silane. And on the C, we just did some nitric acid bait procedure, and only after that we just used the silane. So we could see that there is not a big difference between contact angles. So we didn't use the pretreatment protocols that we were trying first. because every time we use pretreatment protocols, it means that we need to put this another agent into microfluidic system, then pump it, then clean, then change the reagent, and it's always time. And our main purpose is just to save the time without any a lot of to save the time to short the experiment. So here are results. You could see here representative images of hydrophilic and modified chips. There are hydrophilic without any modification because siliceous is always hydrophilic as it is. And this chip was after hydrophobization. So there are different stages of the experiment that are presented here, and additional observations indicate that saline treatment was especially non-uniform, which is consistent with a phase-controlled accessibility mechanism underlying the proposed approach. So on the first stage, we just put in the water, and nothing changed in the chip without modification and with modification. We can see just the water. Why it's green? Because there is a special color for it. Then we've just put the oil to replace the water. And here you could see that on hydrophilic chips, the stage of the water displacement by decant was something like 52%. But displacement of the water by decant in the same chip, but with after modification, was quite the same, 57%. So the final stage of the experiment comprised secondary displacement of oil by water flooding of the micromodel. So we could see that during displacement of decant by water, the water fraction increased to 78% in the hydrophilic chip, which is quite good. But in the hydrophobic chip with a complex wettability, we could see that during the during this water flooding stage, we can sweep efficiency only 45%. So there is a great difference between fully hydrophilic chip and partly hydrophobized. So there are some photos or fragments of a chip after wettability modification. I will not tell a lot about it, but if you would like to know more, there is some text here about this dirty parts of a chip. So in conclusions of this part, we've just created a methodology for generating reservoir-like heterogeneous wettability and microfluidic chips via controlled salinization. And we've just achieved selective modification of pore surface. As a result, exciting hydrophilic and hydrophobic domains are formed with a single microfluidic system. And what would we like to do further? We would like to we would focus on quantitative characterization of wettability distributions. So maybe we would use some nanoparticle systems, extensions, and create other methodologies with another chemistry. So this part was about the microfluidic technology for chemistry modification, but we have another type of technology here. We've just can crystallize some metasomatic minerals. Metasomatic minerals is just the minerals that could be crystallized from the water solutions, and calcium, one of this is one of the examples. So microfluidic models are widely used for flow in porous media, but their surfaces differ from natural rock mineralogy. And sometimes we have just carbonate reservoir, and the oil is situated inside of the carbonate rocks. So the property of this type of rocks are different than others, and it's important to try to just to make the same structure inside of a chip. So there are a lot of different articles how to create carbonate calcium inside of the chip. So we've just created our own methodology and for just oil flow tests, to do them in micro models that can be run at the exact temperature and pressure of the target formation. So the system for forming a mineral layer is quite the same as the previous one. So I would not tell a lot about it. It's just the same. We have the chip and the platform, sensors, and 3 pumps. So the type of formation of the layer of calcium carbonate, the whole methodology is quite clear, and there are two main stages. First stage is seeding crystal nuclear, and we just take the calcium hydroxide solution, we just pump it through the microfluidic chip, then we heat it, and so we combine mild alkaline activation on the channel walls with a anchoring. So then alkaline etching comes, uh, and ions smartly attack the silicon dioxide. So as a result, we just achieve the seeding crystal nuclear. And the stage second is about the growth on the mineral layer. Because we already have the seeding crystals, we saturate calcium bicarbonate, we pump it inside of the chip, then we do thermally decomposition, releasing carbon dioxide and gas excited transport. So as a result, we just have self-regulating deposition. More permeable zones, the local pressure is lower, so the solution reaches its boiling threshold first. So here is the microfluidic chip that we were trying to make by this technology. We follow one chip through the entire process. The bare, there is just the pore network model. Then we seeded it with calcium nucleation sites on the first stage. Then we grow into a continuous classic layer on the stage 2, and then we've just achieved the whole, we just did the oil test. So with a controlled temperature and pressure. Of course, you could see here that not all of the surface of the microfluidic chip is covered by the calcium. It happens because the technology is in such a way, so those type of channels which are closed, the solution just don't go there. So the worse permeability we have, the worse technology like we achieve in the chip. So here is the analysis of the research. The mineralization chip showed 84% coverage through contrast analysis, and the glass has been peeled off, removed from the chip, because otherwise we can't do SEM and Raman spectroscopy. We still have the glass on the top of the chip. And after removing the glass, we can research the silicon substrate by SEM and Raman microscopy, which revealed that the resulting materials was predominantly calcium carbonate in the calcite modification. So this is the conclusions of the work. We've just created two-stage heated flow through methods, grows a continuous mechanically stable calcite layer in a chip, which is quite good result because previously we didn't find any materials with a very good cover. And this uniform coverage results have been presented on Interport 2026 in annual meetings. Of course, we've just have SEM, which confirms continuous integral calcite crystals in the chip, and the platform delivers a reusable laboratory analog of carbonate reservoir that's replaced drilling and core extraction for pore scale fluid rock studies. And in the future, we will try to create another protocols for magnesium and ferrum biron carbonate analogs like dolomite, ankerite, siderite, and other minerals which are carbonate too. So that's all. There are some references, and maybe if you have some questions, I would be happy to answer them.
Yeah, thank you. Thank you a lot, Margarita. It was really, really, really interesting. So I'm suggesting all the people connected online who have questions just to post them, and then we will read them out loud. And while we wait for some questions to come, I will start with some of my own. It was really, really great. So I have a first curiosity related to the first part of your talk, so the modification of the wettability. And I was wondering, just out of curiosity, if you can like modify just the wettability in some portions of the micromodel and like keep different types of wettability within the same micromodel, or if everything is, let's say, modified in the same way, the full system?
the process works in such a way that even I would like to modify all of the pore network model, I would not. For what reason? Because when we just do the same pore structure as in the core, we always have such pores which are ended somewhere. And the fluids just don't goes there. The permeability is very low. We have 155 milliliter C permeability here. And of course, some pores, they are full enough and another one, no. So we can change the flow rate to change the percentage of modified pores. And it is quite a good idea, but it's not always about full modification. We can just control how many pores we full by modificator and how many pores are just filled by the water and nothing else.
Okay, I see. Yeah, very interesting. And then about like the second part of your talk, so this precipitation of carbonate minerals. I was wondering, how do you control, let's say, that the precipitates, they grow up to the full height of your micromodel? I mean, do you just wait enough time or something like that? Or do you have another way to control that it reaches and, let's say, fully grow in the space, in the vertical space?
We control it using microscope. Of course, we can just make the experiments using our equipment. And here is the microscope, which is situated at the top of the microfluidic chip holder. So we could real time show how do these crystals growing.
Okay, so you follow the full growth stage basically with microscopy of the full system. So you have like the whole.
First of all, yes, and the second one we measure is the permeability pressure. So we have the pressure sensors on at the start of the line and at the end. So we can see the difference in permeability. Every time the crystals grow, the permeability just become lower. So we can achieve the proper permeability of the carbonate reservoir because we know it's by the microtomography data, we know this permeability. And then the only thing that we need to do is to wait when our crystals would be big enough just to lower the permeability till this till this parameter that we already have in a core.
Okay, great. Yeah. And then I was wondering, I mean, you were saying that from your Raman spectroscopy analysis, you get that most of the material is calcite, right? Is crystallized as calcite. I was wondering, do you have a way to control if you want like other phases of calcium carbonate, like if you want amorphous carbonate or if you want butterite or other types of that specific mineral?
Yes, it's a big research. The thing is, we can crystallize everything in a chip, but there are some circumstances. I don't know for what reason all of the process of crystallizing comes in a different way as we used to. So I'm PhD in mineralogical science, but when we were crystallizing the same minerals in the volume, which is big, we had the absolutely different picture. When you try to crystallize something in a very small pore structure, it always happens in a very interesting way. For example, in this case, we could see that there are some blue zones here. These blue zones just happen because the gas which came from the second stage, there is no any way to go it out of a chip. So some zones are not filled by the calcium because this gas just stayed here and no way to come. And it's just refuse the crystallization process, just stop it in these zones. So many things happens. We need to study it a lot. And of course, we would like to try to classify another different options of the calcite, even metasomatic minerals, and even I assume we could try to crystallize quartz.
Okay, that's really super interesting. Yeah. So do we have other questions in the studio?
I have a question regarding the second part. It's certainly really interesting. I have two questions. The first one is that do you have any way to characterize which kind of calcium carbonate you are precipitating? Are you sure the polymorph that you are precipitating is calcite, or it could be laterite or something else? And the second question is from the porous media and flow perspective. Do you have any way to characterize how your minerals will nucleate and grow in the Z direction? Do you feel that they will fill the channels uniformly, or do you see any difference in the pattern that they form, and then you see a stochastic aspect in that regard as well?
Okay, answering the first question, we at the process when we're just searching what is happening in the chip without any expectations, we just don't have a lot of ability to just control which type of the mineral is growing, because all of that we have is just the optical microscope. So we can just only create the methodology and always do the same. And by creating the methodology, we can control the type of the crystal after analyzing the results. So we can use contrast analysis, SEM and Raman to control the type of the crystal. We've just choose that first, we've just created this methodology, and then we just do the same. And after a couple of chips, we assume that this is the same mineral because we've already checked it, and so this methodology gave us results. So this is an answer on the first question. Of course, we can be sure at the moment of the growing which type of the mineral grows. Answering the second questions, it's all we don't achieve the cover which is absolutely the same everywhere, because here you could see this pores without any calcite, and moreover I will open the picture of the chip in the first part because the structure is quite the same. So we have two inputs and one output here. So in the channel where which is quite big, and we have a lot of filtration here, of course we always have the bigger layer of the calcite. But it's okay because we do this channel wider and bigger than others. This is bypass of the chip, and we just always do it because we don't want to wait days till all of this fluid come to this small structure. So we just control it. We already know what should we expect, and we make some channels bigger and larger than we need to. That's all.
Thank you so much. Thank you.
It's great, really. So I think that now we can move to our second speaker, and thank you again, Margarita, for this really nice talk. So our second speaker today is Artem Filatov. Artem is a master's student in petroleum engineering from Skoltech, and his research interests include microfluidics and colloid physics. Today, he will specifically talk about the synthesis of oil in water nanoemulsions on a micromixer chip. So with this, Artem, the floor is yours.
Thank you very much. I would like to start my speech with introduction and with a brief definition of what is emulsions, what type of emulsions we have, and describe the mechanism of emulsification that I used in my research. Actually, emulsions is a mixture of two immiscible liquids, oil and water, where one of liquids is dispersed as a small droplets in another liquid. As far as oil and water are thermodynamically incompatible with each other, we must use emulsifier to stabilize this system. There are a few types of emulsions. It can be microemulsions, the most common type of emulsion, milk, for example. Size of droplets in this emulsion is 100 micrometers. But the problem with these emulsions, they are thermodynamically and kinetically unstable. Therefore, for example, when we see on the milk, we always observe the creaming in a few days. Sedimentation is a big problem with macroemulsions. They are unstable. Another one type of emulsions, nanoemulsions, they are kinetically stable. Therefore, we are much more interested in this type of emulsions. Nanoemulsions have the size 500 nanometers, and these emulsions are very interested for us because they are kinetically stable, but they're thermodynamically unstable. By the way, they can be used for encapsulation of vitamins, for example, and because of very high surface area of this emulsion can give us high bioavailability of these vitamins. Therefore, we are interested in synthesis of these nanoemulsions. We can synthesize this via different approaches and can be high energy and low energy methods. And on the next slide, I will explain methods that I used. I use spontaneous emulsification. It's low energy approach. Why I use low energy approach? Because it's less damage the encapsulation and less damaging for material that I want to encapsulate. The spontaneous emulsification mechanism is very interesting. The main idea of this approach is that we load our oil part with big amount of surfactant. When it's on the left part on the slide, you can see on the image. The first image that describes the mechanism. We bring into contact the oil phase that contains a lot of surfactant and the water phase. Then, when this phase is connected, that creates non-equilibrium condition. The interface, the surfactant go to the interface of oil-water contact, and because of this flux of surfactant, the interface became unstable, stretch, and can break into droplets. And this is actually the idea of spontaneous emulsification. Spontaneous flux of surfactant from oil to water and generation of droplets. During preliminary literature review, I found a few advantages of using microfluidics for this emulsification. Microfluidic can help me from the point of acceleration of this process, because in microfluidic chip, I will have a very developed interfacial contact, and I will decrease the diffusion path between surfactant. I will decrease the diffusion path. So yes, I can accelerate this process on the one hand, and on the other hand, possibly I will reduce the amount of surfactant required for this process. But on the other hand, from the literature, I find that during the microfluidic spontaneous emulsification, some studies observed gel formation, so-called gel that can plug your microfluidic chip, and it will be not permeable. It will completely clog the porous media. Therefore, the goal of my research on the next slide is to try to synthesize nanoemulsion on the microfluidic chip and to solve the problem of gel clog formation. The objectives of my research are present on the slide. On the next slide, I show the preliminary batch experiment that I conducted. I just created oil phase with different surfactant concentration. SOR, surfactant oil ratio, COR, is an important metric to just explain how much surfactant in my oil phase I have. For example, surfactant oil index equals to 0.1. In this case, in my final, system, I have 10% of oil and 1% of water. In each experiment, I held constant 10% of oil. For example, surfactant oil index 1, it means that concentration of surfactant is 10 weight% and concentration of oil is 10% also, so the same weight concentration. So yes, I conducted a batch experiment, and as a result of this experiment, on the next slide, I show few potential challenges of synthesis nanoemulsion in the microfluidic chip. Challenge number one is the gel formation. The gel that few researchers told before on previous articles in the literature I found. When I add to the water some amount of oil that contain surfactant at high concentration, surfactant oil ratio of 1 or more, I observed the gel formation. I mean, this droplet don't dissipate in the volume of water, but make this gel particle that don't want to dissipate for a lot of time. And I believe in this gel particle can block my microfluidic channel, and I need to solve the problem with this gel formation. And the second challenge is instability of oil phase with low surfactant load. Surfactant oil ratio less than 0.5 produce unstable system because twin 80 surfactant that I used in my experiment is insoluble in MKT oil in this concentration range. It's highly hydrophilic. So therefore we heated our oil phase, oil with surfactant mixture till cloud point temperature to be sure that our oil phase is stable. On the next slide, I show my microfluidic chip that I used in the experiment. On the left part of the slide, you can see the drawing of this microfluidic chip. Main idea is the Koch fractal principle. This microchannel improve mixing by transforming a straight laminar flow into the chaotic advective flow with constant stretching, folding, and flow splitting. And this mixer was found in the article with modeling of mixing in one article, and they stated that this microfluidic mixer, this geometry will have very high mixing efficiency. So therefore we used this structure. Also on this slide I show equipment that I used in the experiment. It was high pressure lab advanced pump, the lab advanced microfluidic chip holder that will let me to heat my microfluidic system, and the dim light microscope that I used to record a video of experiment. On the next slide, I show the synthesis of oil and water emulsion at the room temperature. We tried to synthesize at the room temperature, but as you can see on the right part of the slide, the pressure evolution profile show constant oscillation. It's constantly jump and go down. It means the constant gel formation, constant plugging of my microfluidic chip. And we did not get the stable pressure during the synthesis. Therefore, we decided to heat our system, because during the batch tests, I observed that when I heat my oil phase, heat my water phase during the synthesis, this gel plug very quickly dissipate in the volume of water. Therefore, we decided to heat, and on the next slide, I show the synthesis during the heating. We observe that during the heating, the pressure very stable, and we got some samples during the pressure stabilization. The total flow rate was 0.01 milliliters per minute, 10 microliters per minute. And we heated our microfluidic chip till 100 degrees, because this 100 degrees is the temperature in which oil phase was stable. And but on the next slide, you can see that this regime, 10 microliters per minute, don't provide complete wetting of the microfluidic structure. I mean, the flux of fluid slip along the interior cavity surfaces. So interior cavity surface. And therefore we decided to increase the flow rate 10 times and 100 times, and to play with temperature, to decrease it a bit till 90 degrees. And as you can see, when we increased the flow rate of our fluids, now all cavities was wetted by the flux of the fluid, and the fluid itself became less turbid. It's less scattered the light. It means that more droplet of oil in water are in nanosize range. Then we conducted, we made some experiment, 5 experiments I show on the slide. And we conducted dynamic light scattering measurements of the sample, and I observed that sample, number C sample, with surfactant oil ratio 1, temperature of synthesis 90 Celsius degrees, and total flow rate 0.1 milliliters per minute, led me to generate nanoemulsion with small Z average size, like 62 nanometers, and very small polydispersity index in comparison with other samples, 0.165. So based on this data, we can conclude that microfluidic synthesis at the elevated temperature of nanoemulsion can be conducted, can be not only conducted, but can provide nanoemulsions with good value of the average size and polydispersity index. And on the next slide, I show conclusions. The main conclusion that microfluidics synthesis of nanoemulsion at elevated temperature works, but future work plan is to find the lowest value of surfactant oil ratio, the lowest value of surfactant that led me to synthesize nanoemulsion. Also, I will try to find the lowest temperature that led me to synthesize nanoemulsion without gel plugging. Then also I will assess the long-term stability of chip-produced nanoemulsion, because I did not do this by this time. And I will evaluate, finally, the encapsulation efficiency of lipophilic, hydrophobic active compound in this nanoemulsion. That's it. Thank you very much.
Thank you so much, Artem, for your talk. Very, very interesting work. So again, I'm encouraging all the people connected online. If you have any question, curiosity, just post it on our YouTube channel, and then we will read them out loud. And meanwhile, while we wait for some questions, I will start with one curiosity. Maybe I just missed it, but like you were saying that using microfluidics, you enhance the process, you accelerate the process because you enhance the mixing in the system, and that's also why you use that fractal geometry, right? And I was wondering, how much faster is the process? Is this spontaneous emulsification that you get in microfluidics compared to a bulk system, for example?
On the one hand, we provide constantly renewing interfacial area. Therefore, I believe it's accelerate the process. But I think the main point here that we can decrease the amount of surfactant.
Okay.
Like in the future work, yes, because we have small capillary, and this decrease the diffusion path, constantly renewable surface area, so interfacial area. So maybe a low amount of surfactant can be used to produce nanoemulsion.
Okay. So it's more like the efficiency in terms of material use of the chemicals more than the.
In terms of decreasing the amount of surfactant and to make these emulsions on the level that will be able to consume by the person. Yes.
Yeah. Thanks. And another point that maybe I missed during your talk, like you were saying that you were like doing all of this process in microfluidics at high temperature, right? And then you optimize the temperature a bit. I was wondering, did you also do it at different pressures, or is that also a parameter that is important to control? Maybe you said it and I just missed it.
I logged pressure during the synthesis, but the pressure here was, what's number slide, 26 slide. I logged the pressure during the synthesis at room temperature, and as you can see, we observe constant oscillation of the pressure, because we have constant gel plugging, gel clogging, and gel, and like, yes, because we constantly decrease and increase permeability of our microfluidic chip. But on the next slide, when we increased the temperature and solved the problem of gel plugging, we see approximately 0.51 bar is the pressure, like exceed pressure on the pump.
Okay, but like, have you tried? My question was like, have you tried setting the pressure first, let's say, and I don't know, like at a higher
back pressure regulator, yes, and to try to set on different pressures? Actually, I didn't think about it. Thank you very much for your question. Why we don't work at different pressures? Actually, previously, I didn't think that pressure can somehow influence the process of emulsification. I believe it should not influence in our
I don't know.
Pressure range.
It's just
In
just
our
a
pressure
curiosity,
range,
really.
in our pressure range, I believe it will not have a high amount of influence, highly influence. But I will think about it more. Thank you.
Okay, so thank you again. Do we have other questions in the studio? No? Okay, great. So with this, I thank you again, Artem, for your great talk, and I think we can end today's session. So before closing, let me just thank again our speakers, so Artem and Margarita, and as well as all the people attending today's seminar, and my colleagues from the Porosity Time Talks, and Mohammad, of course, for leading today's session with me. And well, stay tuned for our next session, which will take place on July 28th. We will have two great speakers. I will get it wrong. Yevgeny Markin from Istopor, and then Mohammad Salehpour from McMaster University. So stay tuned for that. And I remind you that in case you are interested in delivering a talk at with our platform, of course, you can just drop us an email at porosity-time-talks or ttt@gmail.com. So until next time, I wish you all a good evening or morning or time of the day, depending on whether or where you're based. And with this, we end today's session. So thank you again. Ciao.
Bye.